in induction generally we are going to, so suppose you have a graph on n vertices, right. So, you delete a vertex. Now, you have a graph on n minus 1 vertices, and here is a vertex. This is the original graph. So, always you start from an n vertex graph where you want to prove something, right, and then use your induction hypothesis. So, let us say I delete a vertex and I have a graph on n minus 1 vertices. This graph does not have any triangle. So, the number of edges here is at most n minus 1 whole square by 4, but there are a lot of edges like this. What and how many edges? What sort of edges can there be? All we know is that graph is no triangle, right? So, this graph is no triangle, and by induction hypothesis it has at most n minus 1 whole square by 4. But now, I have these kind of edges. How many? There can be up to n minus 1. Can you have all possible n minus 1 edges here? If you have n minus 1, then this number is much more than n square by 4. Right? You have to use the fact that there are no triangles. So, if you have an edge here, then the endpoints cannot have edges to both the endpoints, but if you do not have edges, it can have. So, how do we handle this? Okay, so I think I will go back to my slide. So, the simple trick here is, so this is something very useful. You do not delete one vertex, you delete two vertices, and you delete two vertices which are adjacent, and then you get some handle on it and you can do something. Now, you have a consider a triangle free graph on n plus 1 vertices. Suppose this is a graph with the maximum number of edges, because I want to show that the maximum number of edges possible is at most n square by 4. So, look at a graph on n plus 1 vertices, maximum number of edges, it is triangle free. Now, I pick a pair of points such that they are adjacent, okay, in the graph. Why should there be such a thing? Well, if it does not, there is no edge at all, the number of edges is even 0. So, it is good, right. So, pick an edge. Now, let us go back to the induction and see how we can use that. So, I am not just going to delete one vertex, but so I picked a pair of points. This is a graph on n plus 1 vertices, and I will delete these 2 points, right. Now, there are n minus 1 vertices here, because totally there are n plus 1 vertices, and this has no triangle inside. Now, this has no triangle. So, how many edges are here in this graph inside? At most n minus 1 whole square by 4. Now, let us talk about the maximum number of edges between. How many can there be? The fact that I picked an edge is going to give me a handle, right. So, suppose this vertex is adjacent to, let us say, somebody here, then this vertex cannot be adjacent to that, right. So, what is the maximum number of edges possible between these two? Because it is not, there are no triangles, some u is adjacent to somebody, v cannot be adjacent to somebody. So, what is the maximum number of edges possible between the two? There are n minus 1 vertices here, I better use them and have all edges. We are trying to maximize the number of edges. The only condition is, because of the triangle free condition, if u is adjacent to somebody, v cannot be adjacent. So, between the two they choose, okay, I am going to be adjacent to some 50 and you are adjacent to the remaining, right. So, that is the maximum they can get. So, the number of edges between would be at most n minus 1, plus this is an extra edge. So, the total number of edges possible is at most n minus 1 whole square by 4 plus n minus 1 plus 1. This, hopefully, if you sum, you should get what you want. Let us do n square by 4 minus n by 2 plus n. So, plus n by 2 minus 1, because this is plus 4. So, plus 1, this cancels. So, there is plus 1, and this is hopefully, so it is actually plus 1 by 4, right. Yeah, minus n by 2 plus n. So, it is n by 2, this cancels, yeah. That is exactly what we wanted. We are looking at a graph on n plus 1 vertices, right. Simple induction. The only thing is, you shouldn't just delete a vertex. You have to be a little careful, because you are not getting a handle if you just delete a vertex. You delete an edge, then when you delete it, you have this. Okay, and that's what the proof completes. Okay, so now this is a proof, right? Complete bipartite graph n by 2 is one construction. Now this actually tells you that every graph, if it doesn't have a triangle, you can't have more than n square by 4 edges. I'm going to give you a couple of more proofs. Okay, so here is a very nice proof which I liked. Yeah, so suppose dx is the degree of a node x, then what can you say about dx plus dy? For if xy is an edge, we already saw this actually. Dx plus dy can be at most how many? 2e. Triangle free. Remember, we are using the fact that this is triangle free and xy is an edge. So xy is an edge. So how many edges can they go out of xy to the remaining? We already saw this. So totally there are n vertices. So n minus 2 edges can go out, plus you have to count for this 2 degree, right? If you look at the degree, this is 1 degree, this is 1 degree. So totally n, right? Is that clear? So what am I saying? If you have an edge xy, right? I want to count what is the maximum degree possible for dx plus dy. Well, dx may be adjacent to something, dy may be adjacent to something, but they don't have common neighbors because xy is an edge and we don't have triangles. So this number is the maximum number of edges they can be adjacent to. So their degree dx plus dy is n minus 2 plus 1 plus 1. So it's at most n. Okay. So now let's look at this quantity summation dx whole square. Just like that, I want to sum this and see, get an upper bound for it and lower bound for it, and together we will get something. So q is the number of edges in the graph. I should have used m, but okay. So now one way to think about this quantity summation dx square is that for every vertex x, there are degree many edges going out, and suppose I add a weight of dx to each of these edges, then I am adding the sum of the weights on the edges, right. So just look at one entry dx whole square. It's basically I take a vertex, I look at a vertex x, and it has dx many edges going out of it. So I throw in a weight of dx here, dx here, dx here, dx here, and add the weight of these edges. That's exactly dx square, right. So suppose I do it for every vertex, then the summation dx square I am going to translate to something on the edges. So suppose you have an edge xy, what is the weight on that edge? No, if you have an edge xy, what is the weight on that edge now? Dx plus dy. X gives you dx, y gives you dy. So the weight on the edge is dx plus dy, right. So this is same as for every edge, just add dx plus dy. Okay, this is a very nice, just different way of looking at it. I am just computing this sum, and this is exactly this sum, right. Now, but dx plus dy for any edge we know is upper bounded by n, right. So this gives you, it's at most n times q. Okay. Some quantity I was interested in, summation dx square, and I could show that it's at most qn using the fact that it's triangle free. Where did we use the fact that it's triangle free? Because we used it here when I said that dx plus dy is less than or equal to n. Here is where I am using the fact that it's triangle free. So this quantity is qn. So now I want to give a lower bound for summation dx square. But what do we know about summation dx? 2 into number of edges, and so we can give a lower bound for summation dx square. This is a very, very useful inequality that shows up. Suppose you have some, let's say 2 numbers that add up to 10, and I want a lower bound for the sum of the squares. What is the minimum number for the sum of the squares of the numbers? 2 numbers add up to 10, I don't know what the 2 numbers are, okay. It could be 4 and 6, it could be 3 and 7, it could be 5 and 5, it could be 8 and 2, whatever. Now I want to know what is the sum of the squares. I don't know it exactly because I don't know the numbers, but I want to give a lower bound for the sum of the squares. Then it turns out you can use some standard inequalities. When all the numbers are same, that's when you get the minimum. Okay, so just work it out, right? 5 plus 5, so 25 plus 25, 50 is the sum of the squares when the sum is 10, when it's 5, 5. But if it's 2 and 8, you get 64 plus 4, And if it's 3 and 7, you get something else. So 5, 5 is the minimum. So similarly here, the sum of the squares attains its minimum when all the numbers are same. So what is the average dx then? If summation dx is 2q, then the average dx would be 2q divided by n, right? Because there are n vertices that add up to. So 2q divided by n, so that is 2q divided by n whole square, summation dx square. You are adding it over x, but there is no x at all in the term inside. So you can multiply by n. The whole thing gives you 4q square by n. So we have a lower bound for summation dx square, which is 4q square by n. We have an upper bound q n. You put them together and you get what you want. 4q square by n is less than or equal to qn. So q is less than or equal to n square by 4. Right? Is it clear? 3-line proof, really, right? There's nothing going on here. Simple result, just really 3 lines, but it's very cute. Somehow this concept of do the summation dx square, distribute it, add it over edge, use this inequality, use the lower bound, upper bound, done. Here is another proof which actually gives you something little more than what we want. Okay. Let A be a maximum independent set in the graph. Okay, it's not an algorithm question. I don't need to find it. Let's assume that look at the maximum independent set. Okay. What can you say about neighbors of every vertex? Take any vertex. Look at their neighbors. Can there be an edge between any pair of them? Why not? Because it's a triangle free graph. We are looking at a graph where there is no triangle. So take any vertex and look at all its adjacent vertices. They must be independent. There cannot be an edge between any pair of them. So the degree of any vertex is at most size of cardinality of A. Right? Because A is the maximum independent set. Okay, so let B be equal to V minus A. Now, since A is independent, every edge should have at least one endpoint in B, right? Because you cannot have an edge inside A. Okay, so now I am going to count the number of edges slightly differently. If you sum the degrees of vertices of X alone, number of edges is upper bounded by that. Why is it upper bounded? Why are they not equal? Okay, I think it needs a picture. So A is the maximum independent set and B is the remaining vertices. Okay. So every edge has some endpoint here. All the edges are here, either here or here. Right. So if I do summation dx x in B, this accounts for all the edges and more. More because some edges inside B are counted more than once. So the number of edges, this is greater than or equal to number of edges because there are no edges inside here. Agreed? So total number of edges is at most summation dx x in B. But we already have an upper bound of degree of any vertex. We know that it's at most size of A because every neighborhood is independent and A is the maximum size independent. So this is less than or equal to summation cardinality of A x in B. So this means that this is equal to cardinality of A times cardinality of B. So number of edges is less than or equal to cardinality of A times cardinality of B. Here is another beautiful inequality that's very handy. This is the geometric mean of two numbers. Okay, if I put the square root of it. And what do we know between arithmetic mean and geometric mean? Something you learnt in your high school. Arithmetic mean is always greater than or equal to geometric mean. Okay, so cardinality of A into cardinality of B square root is the geometric mean of these two numbers. So this is less than or equal to the arithmetic mean, which is cardinality of A plus cardinality of B by 2. But since square root is really the geometric mean, so this is less than or equal to square of this. But what do we know about A plus B cardinalities? N, right? This is the entire partition. Lo and behold, we are done. This is what we wanted to show, right? There is some independent set. Look at something. Now, this proof gives you a little bit more, because you can ask the question, when we already saw this, you can ask the question, where, is there a graph where the number of edges is actually n square by 4? This only tells you it's always at most n square by 4. He already told me in more, at the beginning that complete bipartite graph, but this proof will give you when is q equal to n square by 4? Well, if all these inequalities are the same, right? If they are actually equal to. When is this equal to? If there are no edges here, right? Because if there is an edge here, then that edge is double counted in the degree. So, this is equal to if both these sets are independent, and this is equal to geometric mean and arithmetic mean are equal when the numbers are the same. Okay. So, you take a complete bipartite graph on n by 2 vertices, n by 2 vertices, that is the one that achieves the maximum number of edges. So, all this fits into this whole area of extremal graph theory, where one is interested in some property of graphs which don't have this, what is the maximum number of something, minimum number of something. These are some very useful results, they come handy in many applications. And so this proof not only gives a bound, but also shows that the extremal graph is a complete bipartite graph with each part having almost equal size. Okay, almost, because n may not be even, right? So, you can't say n by 2, n by 2. So, just the difference of at most 1. Okay, good. That's a set of proofs for Mantel's theorem. Now, I want to just look at a generalization of this, which is Turan's theorem. Okay. So, Turan's theorem, how is it a generalization? It just wants the number of edges in a graph. So, a triangle is a clique on 3 vertices, right. So, now I can ask the question, what about the maximum number of edges in a graph which does not have a clique on some number of vertices, right. So, suppose you have no clique on m plus 1 vertices, then the theorem says that the number of edges is at most n square by 2 minus n square by 2m. Now, can you think of the construction? I mean, you all said, oh, if you don't have triangle, it's complete bipartite graph is one graph that achieves it. If I don't have a clique on m plus 1 vertices, what sort of a graph? Well, I've given a hint here, right? M equal to 2 actually gives Mantel's theorem, because number of edges in a graph with no k3, which is a triangle. So, if you want to generalize complete bipartite graph, complete m-partite graph, right. So, take m independent sets and draw all edges between them, right. Can it have a clique on m plus 1 vertices? It's each part, there are m independent sets of equal size or not doesn't matter really, we will come back to that later, but and I have all edges between every pair of parts. Now, can it have a clique on m plus 1 vertices? Well, if you have to have a clique on m plus 1 vertices, it must pick 2 from one set, right, pigeonhole principle. There are only m sets, and if you have a clique on m plus 1 vertices, you must pick 2 from one set, but each set is independent. So, that is one graph which does not have m plus 1 sized clique. So, you have m parts and no edges inside, but there are all edges are across. Okay. How many edges are there? Well, let us compute. Totally there are n vertices. So, that is n choose 2 edges minus edges inside, right. So, let us say all of them are equal and n by m of them. So, it is n by m into n by m minus 1 by 2, that is the number of edges inside which are missing, right, because each one has n by m vertices and m of them. So, this m cancels, and this is the number of edges in such a complete m-partite graph, because all possible edges are there except the edges inside each part, and it turns out if you do the calculation, this is exactly that number which we are trying to